Welcome and thanks for clicking on my IMAC presentation titled Balancing Impedance and Controllability in Environment Testing. My name is Matt Tuman and I'll be presenting on behalf of my co-authors, Professor Matthew Allen, Washington DeLima, Eric Dodgen, and Jonathan Hauer. So first I'll give a brief background of the motivation and methodology for our work. So ideally, you would like to know if a part or structure will break before putting into operation, which is the reason for environment response reconstruction testing. One of the current standards for this type of testing is to use accelerometers to measure the operational response of a previously designed structure. An example of this would be using accelerometers to measure the operational response of a rocket at key locations on the structure during launch. Then these acceleration measurements are used to define an environment in the form of power spectral density profiles. Then a single axis shaker, as shown here, is used to reproduce these acceleration profiles to determine if a newly designed part can survive its intended environment. So the main goal of our research is to perform a reconstruction test that reproduces the response of a subcomponent by controlling only to measured responses on the primary structure. So in essence, we try to recreate an environment acceleration and profiles on the primary structure. And if that task is accomplished, we hope that the environment is also accurately reconstructed on the subcomponent, even though we aren't controlling to it. The theory that we use is called the transmission simulator. As a high level overview, we can use the illustration here. So there are three items we always consider. So the subcomponent of interest, the part the subcomponent is attached to, and the rest of the structure, which in this case is a rocket. So we defined that the part that the subcomponent is attached to as the transmission simulator. And because the subcomponent is only attached to the transmission simulator, we can assume that force from the environment goes through the transmission simulator to the subcomponent. And if this assumption is correct, the response of the subcomponent should be completely dependent on the response of the transmission simulator. This means that even if we detach the transmission simulator and the subcomponent from the complete structure, if the modal response of the transmission simulator from operation is accurately reconstructed, the subcomponent response should also match its environmental response. To test our theories and methodologies, we use flight data from a sounding rocket that flew for Kansas City National Security Campus. Inside the sounding rocket was a substructure that contained a dummy payload, which we call the stool and plate, as shown here. For this assembly, the stool is our subcomponent and the plate is the transmission simulator because the stool is only attached to the plate. For this launch, 3 triaxial accelerometers were used to measure the response of the plate, and another 3 triaxes were on the stool, which recorded the response during launch. This subassembly was then sent back to us, and we try to recreate the responses recorded during launch. So we have our stool and our subcomponent, the subcomponent, excuse me, and the plate, which is our transmission simulator. We then use control hardware and a multi-input, multi-output, otherwise known as MIMO, test setup with 6 small shakers to recreate the environment profiles on the plate. It is important to note that the control software is only controlling the response of the plate. The stool is not controlled. And an example of what these profiles is shown here for an accelerometer on the plate. So the black line is the environment acceleration profile we are trying to match. The red lines are plus or minus 6 dB air envelopes of the environment. And the blue line is the response measured during our reconstruction test using our 6 shakers. So as we can see, we do a relatively good job of matching the operational response for an accelerometer on the plate, which is expected because the software is controlling to this. However, when we compare the operational response to the measured response during our test in the lab for the uncontrolled stool, we see that our response accuracy degrades significantly compared to the plate, which is a problem because we reconstructed the response on the plate well, which because it's our transmission simulator should mean that, well, our hope is that the response in the stool would be accurate as well. So our work now focuses on understanding how to predict and improve the reconstruction accuracy for the uncontrolled stool, which is our subcomponent of interest. In our previous work, we tested configuration A and configuration B. The only difference between these two was that configuration B had more of the original structure that flew on the rocket, which is this attached interface plate. What we found for both configurations is that we were able to control the plate relatively well, but the response accuracy of the uncontrolled stool was better for configuration B. And we believe this improvement was observed because configuration B had more similar impedance to the full assembly that flew on the rocket. And we define impedance as the transfer function relating some force input to some output response such as acceleration. So a full impedance match would be achieved if the transfer function were the same between our assembly under test and the full rocket. Thus, because configuration B has more of the operational structure than configuration A, we say that B has an improved impedance match. Ultimately, we noted that improved impedance match resulted in better reconstruction accuracy for our uncontrolled subcomponent. To further test this theory, this current work investigates configuration C, which includes even more of the original structure. For this new configuration, we use the same workflow that was used on our previous two assemblies. First, a modal roving hammer test was performed on the assembly. Then simulations using frequency response functions from the hammer test were used to determine optimal locations to attach our shakers. Then we performed a reconstruction test and analyzed the results. To compare reconstruction accuracy between our different configurations tested, we used an average dB error metric. To compute the error metric, the first step is to average the square dB error between operational profiles and the reconstructed acceleration profiles at a specific frequency. Then the final metric is calculated by averaging the errors computed in the first step over all frequency lines in the bandwidth of interest. So essentially a low error is desirable, and in our case, we found that a dB error of less than 7 is very good. So after performing a modal hammer test, an input selection algorithm was used to determine an optimal set of locations for where we should attach our shakers. For this test, 3 electromagnetic shakers were used, attached to the structure via piano wire stingers. 3 Q sources were used attached directly to the structure via super glue. The other 2 are just on the bottom of this interface plate. And then in accordance with our transmission simulator methodology, we only used our control software to control to the 7 working acceleration channels on the plate, but we still measured the response of the accelerometers on the stool. So here are some of the results from this test. Once again, the black line is the measured environment profile we are trying to match. The red lines are an error envelope, and the blue line is what was measured in the lab during our reconstruction test. So we'll start by looking at the reconstruction results for the accelerometers in the launch direction on the plate. With dB errors of less than 7 for all 3 channels, and simply by visual inspection, we did a great job of recreating the environment in this direction. However, when we look at the response for the accelerometers in the off-launch directions on the plate, we notice that our reconstruction accuracy is significantly worse. So this suggests that it was difficult to control the structure in these directions with the number of shakers we were using. So now that we've completed testing on 3 configurations, we can compare the reconstruction accuracy. As I previously mentioned, for configuration A and B, we were able to recreate the response on the plate fairly well, and we noticed that reconstruction accuracy on the uncontrolled stool was better for configuration B, presumably because it had an improved impedance match. However, for configuration C, we're no longer able to accurately control the plate response, which unsurprisingly produces a higher error for the uncontrolled stool. So why do we observe the results we've obtained? The explanation we are most confident in is that configuration C is simply much more complicated. The figure on the right shows the average FRF for each of the three configurations, with the line colors corresponding to the border colors of the images underneath. So configuration C, being blue, clearly has the most modes, and so you don't have to count them for yourself or put them in the table here. So with 21, configuration C clearly has more modes. And because we're keeping the same number of forcing inputs for all three configurations, it's no surprise that it's more difficult to control C since it has more modal degrees of freedom. This leads into a discussion of balancing controllability and impedance when performing this type of test. Our prior work suggests that simply adding more of the original structure would improve the response accuracy on our uncontrolled subcomponent. But now we've learned that controllability of a system must also be assessed. It appears that a sweet spot exists for choosing how much of the original structure is to be included, such that the impedance and the controllability are balanced, which in our case would be configuration B, which is where we obtained our best results. Now that we've learned these lessons about this type of testing, we wanted to go back and see if we could have predicted these trends based on simulations using FRS from remote roving hammer tests that were performed on each configuration. So we went back and simulated each of the physical reconstruction tests that were presented earlier. And in the process, we discovered that using a condition number threshold improved our simulation's ability to predict what will happen experimentally. But because I don't have time to go over this in this short presentation, I'll just advise the viewer to reference the paper that was submitted with this talk. So here are the results from the simulations. The dB error for each configuration on the plate is presented with the notation of simulation error slash then the error recorded from the physical experiment. So we're only looking at the errors on the plate, and we see that the simulation predicts that the controller will be able to somewhat accurately reconstruct the response on the plate for configuration A and B. But it also accurately predicts our inability to control the plate response for configuration C, which is evident with this 2 dB error jump in the simulation. So this ability to identify the inability to achieve control for configuration C could be very useful when planning these types of tests in the future. So ultimately, what did we learn? We learned that simply adding more of the original assembly to the testing fixture does not guarantee improved reconstruction accuracy. It appears that some balance of controllability and impedance must be achieved to have the best results for this type of transmission simulator reconstruction testing. Furthermore, we learned that the simulations with a condition number threshold can do a reasonable job of predicting the accuracy of a physical test and could be potentially used to determine which testing configuration is best between various configurations. And moving forward, we're going to try to identify a more robust and reliable strategy to quantify controllability, just because at the moment we're simply counting modes. And then in addition, we're going to explore alternative methods to further improve our simulation's ability to predict the accuracy of a physical reconstruction test. Thank you for watching anytime.